So I'm just continuing along in the course notes here, so if you're following along as well, this is on page 3 of the notes from today. And so at the top here, we're just defining a new matrix. So when we stopped last time was with matrix multiplication, and now I want to define a new matrix. It's called the identity I. And I is defined to be the matrix with 1s along the diagonal and 0s everywhere else. If you want to do 2 dimensions, that would be 1s along the diagonal, 0s everywhere else, and so on. Okay, and the nice thing about the identity matrix is that if you take any matrix A and multiply it by I, or if you take it in the other order, I times A, you just get A back. So it's because of this property that it acts kind of like the number 1, in multiplication, except we're multiplying matrices instead of real numbers. Okay. Now, I also wanted to just quickly define the inverse matrix, because some people have already wanted to use this to solve a system of equations, and that is fine, but this will put us all on even footing here. So if A is equal to A, B, C, D, then the inverse matrix is denoted by A with a -1 on the top, and that is, whoops, I didn't leave enough room for my determinant, 1 over the determinant, AD minus BC. And then for the matrix, if you look at your diagonal entries, you flip those, and then in the other 2 entries, you negate those, so minus B minus C. And so the idea behind the inverse is that we'll do this now, is that A times A inverse is the same thing as A inverse A, and that is equal to the identity. And so let's try one. A, B, C, D times the inverse. I'm going to go ahead and factor out my determinant. D minus B minus C, A. Remember, before I do that, let me just factor that out. Okay, so the first column here is going to be A, B, C, D times our D minus C. And then remember the second column is going to be A, B, C, D times our second column minus BA. Good. And so 1 over AD minus BC times, that's AD minus BC, that's handy, CD minus CD, and then in the second column I have A times minus B plus B times A, which is 0, and then minus CB plus AB, or AD minus BC. I don't know where that mark came from. Good. And so that is the identity. And I will leave the other direction for you if you'd like to check it out. Good. All right. So now, why are we looking at all these things? Well, we want to consider solving the system of equations ax plus by equals e, cx plus dy equals f. Okay. Now when we're solving these, there are 3 possible outcomes that we've talked about before. One is a unique solution, point of intersection you can think of. Okay, and so to solve for that, there are several ways. We already know Cramer's rule. You could also use the matrix inverse, because this is matrix A times xy equals EF. Or you could say A times vector x equal vector B. And so if you look at it this way, you can multiply both sides of your matrix by A inverse. And so then x is equal to A inverse times B. And so your unique solution here is going to be A inverse times B. Now you don't have to memorize that. This is just showing you that there is a direct way of computing that. The second way is that there might be no solution. That is parallel lines. And the third way is when there's an infinite number of solutions, and that's the same line. Okay, now both of these cases come up for when the determinant of A is equal to 0. Because remember, when you're computing A inverse, you need to be able to compute that determinant, right? So the question was up here, if this is, where's my definition? There's my definition. If this is equal to 0, then what can you say? That means if 0, A inverse does not exist. Okay? Which means that you have one of these two cases. There's either no solution or an infinite number of solutions. Okay? Good. So in the case that we do have an infinite number of solutions, let's go ahead and talk about that. If we have an infinite number of solutions, express them in parametric vector, sorry about my handwriting, I'm trying to go real fast, parametric vector form. And so how do you write a line? Write the line, how shall I express the line? How about ax plus by equals e? I'll just write the first line in parametric form. Okay, so well, to do a parametric equation, so just as a note, parametric line, I need a point that the line goes through and a direction. So if I have point P, say, and direction Q, then my line is parametrically written as P plus TQ, where I'm just writing those in vector form. Okay, so how about now with ax plus by equals e? Well, number one, I need a point, and then I need a direction. So I can take any point on this line. Is there a convenient point to take on the line? Probably not. Let's see. How about if x is equal to 1? We could just take that one. And then what would y be? Oops. And then y would be e minus a over b. And then what would the direction be? Well, the slope of this line is going to be minus a over b. And so that is in the direction of, this is rise over run, right? So that's b minus a. Okay, or you could say if the slope is m, then you could have 1m. Either way, those are pretty much equivalent, just scalar multiples of each other. Okay, and so with this point and this slope, you could write then that my vector is, this is kind of complicated, plus t times my direction, b minus a, say. Okay, so you can see this is a lot easier if the line goes through the origin, because then this would just be 0 and you would just have that. Very good. Okay, so just as an example, right, x plus 2y equals 3 in parametric vector form. Go ahead and pause for a moment. Okay, so if I let x be equal to 1, can I get y then? Let's see, 3 minus 1 is 2, y equals, oh, hey, how about that? Then y is equal to 1, and then my slope is minus 1/2 in this case, right? So therefore I can write 1, 1 plus t, and then rise over run would be 2 minus 1, right? Good. And so I'm going to stop here, and we will continue on. We made it through page 3 now. This is going to take a little while. Sorry about the link.